Hello, my dear. Welcome to IMS GATE Academy. I hope you are all good and your preparation going to be in a right direction. I am Pragyabrat Tripathi, faculty of IMS GATE Academy. So, my dear, we will continue with the subject of thermodynamics. So, we already discussed that what is the system surrounding all the things. First law for closed system, how to apply the first law, what is the practical application what is the practical consequence of the first law of thermodynamics. All these things we have already discussed. Now today we will discuss the first law for the open system. That means how to apply the conservation of energy for the open system. That means something is in and something is out. So for that one, this is your we have to apply. This is also done, example also done. Now first law applied for the open system. Now yesterday we'll discuss what is the main assumptions of the first law of thermodynamics. The main assumptions of the first law of thermodynamics that at a inlet cross section and exit cross section, at a cross section properties of the fluid doesn't change. Okay, that means it is uniform throughout the cross section. That means if you select the cross section, that property is fixed along the cross section. Okay, so and we apply the two conservation equation in this. When we analyze the open system energy conservation for the open system, there are two conservation equations. First is the conservation of mass, and second also the conservation of energy. Okay, no problem at all. So there is a we'll already so see this one, beta. See this one. Okay. Okay. So this is your, let's suppose this is your control volume. Let's suppose this is your control volume. Okay. Let's suppose this is a control volume. Control volume. And why, how to make a control volume? There is one inlet section and there is, let's suppose there is an exit section. So this is your exit section and this is your inlet section. Okay, so something is into the system and something is exit to the system. That means this is a E and this is your I. E and I is the cross section. E and I is the cross section. Let's suppose this is the mass mCV, mass of the control volume, and ECV is the energy of the control volume. Okay, energy of the control volume. Now beta, we have to apply, this is the control volume. Now we have to apply conservation of mass. Okay, so conservation of mass. Conservation of mass. What is the conservation of mass? What is the conservation of mass? Mass, if you write rate basis, that means kg per second. Say mass, this is m dot, that is called mass flow rate. Mass flow rate. Okay, and this is your kg per second. That means something is in per unit time. That means mass flow rate at inlet cross section minus mass flow rate at exit cross section is equal to mass flow mass of the control volume. That means dm by dt of a control volume. No problem. Of a control volume. So this is the first conservation equation, conservation of mass. Now beta, see, very important. Now we have to apply the conservation of energy. Okay. Conservation of energy. Okay. So what is the difference between the conservation of, when we apply the conservation of energy of the closed system and when we apply the conservation of energy of an open system, what is the difference? See beta, the conservation of energy, that means first we discuss, see, let's suppose there is heat is into the system and work is out from the system, that means control volume. Okay, this is heat, let's suppose this is dot and this is dot. So this is heat into the control volume and this is the work out from the control volume. Let's suppose there's a positive sign. So what is the conservation of energy equation? What we know that the conservation of energy? We know that energy in minus energy exit is equal to energy of a control volume. Yes or not? This we know that. Yes or not? This we know that. This is the conservation of energy. But see, this is the transfer of energy. This is your transfer of energy, net transfer of energy, and this energy transfer is due to heat, work and mass. Okay, and this is your change in energy, and this change in energy is in the form of internal energy, kinetic energy, potential energy. Okay, so this is in the form of internal energy, kinetic energy and potential energy change. Yes or not? That means change in internal energy, change in kinetic energy, change in potential energy. This we have know already. Now my dear, see the beauty, see the beauty. This is the energy in, this is the energy out. Okay, so this E is what? Is the energy which is in due to the either heat, work or mass. Okay, no problem at all. That means, let's suppose their mass is in here m dot I and here mass is exit me. Okay, so energy in is what? Q plus mass. So mass, this mass of the fluid have energy. This is the mass of the fluid. Yes or not? This is the mass of the fluid which is try to be enter, and this mass of the fluid have a stored energy. Yes or not? Store energy. Yes or not? Yes or not? And this store energy, it is in the form of numerous form. So, hi Sita, I am fine. What about you? I am fine, Sita. So, mass of the fluid, and the mass of the fluid is, it is when the mass of the fluid is entered to the system and mass of the fluid is exit from the system, due to that entry of mass and that the entry of the exit of the mass, that mass itself have a stored energy. And this stored energy, that means if there is a mass, let's suppose if there is a mass, I will discuss you, no problem. So if, see beta, if there is a mass, okay, flow rate, that means kg per second, no problem. If there is a mass, this mass have a stored energy. Okay, okay. Mass, and this mass have a stored energy. Stored energy. That means, see, this is a container. In that container, there is a mass. There is a fluid, and fluid have a mass. And that mass of the fluid have a energy. and that energy, it is in the form of stored energy. It is in the form of stored energy. So that stored energy, if there is a mass, so that stored energy, it is in the different form. You already know. Okay, the stored energy. This is in due to the temperature. Due to the temperature, that means internal energy, kinetic energy, and potential energy. You know. So if there is a mass of the system, either this mass is static or moving, so this energy, it is associated, this is the microscopic level of energy. Microscopic level of energy. And this is always there when the fluid either moving or rest. That means this energy always present. Always present. It is no matter the fluid is rest or fluid is moving. No matter. It is no matter. It is always present. Now, if this mass is now moving, that means this mass is now entered to the control volume. Entered to the control volume. That means there have a motion. That means there have a motion. That means there have a flow of mass. Flow of mass. Flow of mass, and that flow due to the pressure. Due to the pressure difference. Pressure difference. Okay, due to the pressure difference. Now, that pressure difference is responsible to enter to the control volume or exit from the control volume. Due to that pressure difference, there must be a flow energy, flow work or flow energy or pressure energy. Like that, beta. See, we already discussed like that. See this one. This is when there something is into the control volume and something is exit from the control volume, there must be a flow energy, that means P into V, that means Pi, Vi, P exit, V exit. This energy will always there due to the mass enter or exit. Okay. So when the fluid is start to moving, there must be a flow work, and that flow work is per unit mass basis. That means P into V. That means if there is the fluid is at rest, only this energy will there, and if the fluid is motion, the extra component of energy will add into this one, and this addition of 4, it is in the form of stored energy. That means if there is a non flowing fluid and there is a flowing fluid. Flowing fluid. The non-flowing fluid, let's suppose E is the energy. Flowing fluid, let's suppose theta is the form of stored energy. E is the stored energy per unit mass basis, okay? That means this stored energy E per unit mass. And this is theta is also stored energy per unit mass. So, this stored energy of the fluid, it is in the form of internal energy plus kinetic energy plus potential energy, yes or not? And for a flowing fluid, it is in the form of internal energy plus kinetic energy V square by 2 plus potential energy, and there is one another form of energy, flow energy, P into V. Okay, so this equation this is one equation and this is your E, this is your another equation, okay? So this is the stored energy, sorry, this is theta, not E, this is theta, okay? This is theta. So this is your stored energy per unit mass when there is a non-flowing fluid, and this is your stored energy per unit mass of a flowing fluid, okay? So beta, we know that this U plus PV, that means this U plus PV, this and this two, if you combine, this is your enthalpy H. So what is the energy or stored energy of a flowing fluid? Enthalpy plus V square by 2 plus GZ. This is your final. Okay, this is your final. That means when there is a non-flowing fluid and when there is a flowing fluid, instead of internal energy, there is a enthalpy. Okay, that means this is your internal energy, this is your stored energy per unit volume, per unit mass. Energy per unit mass, and this is your internal energy, this is your kinetic energy, and this is your potential energy due to datum. Potential energy due to datum, and this is your enthalpy and all are the same. So this is the difference between the stored energy when the fluid at rest and this is the stored energy when the fluid is moving. This is very important. Okay. Now, so beta, if you find energy in, so energy in, it is in the form of heat and mass, and if there is a mass, the mass have a stored energy. What is in stored energy? Enthalpy plus kinetic energy plus potential energy at inlet plus stored energy at exit, mass is exit. So if you write this equation in the form of energy, in the form of this balance, if you balance this, so if you balance this, so what is that? Energy in minus energy exit is equal to dE of dt of a control volume. Yes or not? Yes or not? See beta, this E, see this one, this E is the energy, and this is in the joule or kilojoule. Okay, this E dot is the joule per second, and this is called watt power. This is called watt. Okay, so this is in the form of watt. So rate of what is in heat is into the system, plus what is in mass is into the system. That means Mi along the mass, and this E is what? That means if there is a flow now, if there is a flow theta, that means theta by m, sorry, E by m. This is important. What is E here? This E is the energy, and this is not joule. So this E, if you write theta, so this is your, this is what? This energy per unit mass. So what? So this theta, it is in joule per kg. So what is E? Theta into mass. So if we put E dot, so there is a m dot. No problem at all. So if there is a Mi, so Mi dot into theta I, yes or not? Okay, this is one component, this is in, minus what is exit, work is out, W dot, plus M exit. With the M exit, there is a theta exit. This is out, is equal to dE by dt of a control. No problem at all. No problem at all. Now, what is theta I? What is theta I? Theta I is nothing. It is your Hi plus Vi square by 2 plus Gzi. Okay, this all are in, this is energy in joule per kg. Per kg, that means a specific energy. Okay, so here we can write theta dot plus Mi dot into Hi. So this is your Hi, okay, plus Vi square by 2 plus Gzi. No problem at all. This is in one bracket, minus work plus, this is your m dot exit, H exit plus V exit square by 2 plus Z ZE, okay, is equal to this dE by dt of a control volume. No problem at all. No problem at all. Now, see my dear, this is the equation, you can write like that also, Q dot minus W dot, this is the work output of a control volume, right, is equal to, take that side, dE by dt of a control volume, okay, take that side, and if there is a many inlet and many exit, that means there is a one inlet and one exit, na? Thank you, sir. There is a one inlet and one exit, but there may be a chance that there is a control volume of many inlet, many exits. It may be. So instead of mi1, there is a summation of mi, there is a summation of m exit. So we can write like that, if you put that one, plus summation of exit m, write down this is theta, no problem, m dot theta. This is your exit, okay, this is your exit, okay, plus minus summation of inlet m dot into theta. So this is the first law of thermodynamics for a open system. This is the first law of a thermodynamics for open system. This is very important, I am telling you. This is your first law of thermodynamics for the open system. This is your first law of thermodynamics for open system. So this equation beta, this equation is the first law of TD. This equation is first law of TD for control volume. Okay. So this is also one inlet, either one exit. It may be, it is in this form. Now, that means what is happening, beta? What is happening? That means you have Q dot minus W dot. This is work done by the control volume is equal to dE by dt of a control volume plus what is that? M exit. There is exit. That means summation of at exit m dot theta minus summation of inlet m dot theta. No problem at all. Now, see my dear, we have to take one simplicity. For a simplicity, take steady flow, steady state system. That means we have to take like that. We have to take like that, steady state, steady flow process. Steady state, steady flow process. Okay, steady state, steady flow process. Okay, so what is that? If we do, if we have a mass balance, what is the mass balance? dmCB by dt is equal to summation of all mass at inlet minus summation of all mass at exit. This is the mass balance. This is the mass balance. And if there is this is 0, why? Steady flow, due to steady flow device, yeah, steady device. So what we can say that ki sir, summation of all the inlet mass is equal to summation of all the exit mass. Mass inlet is a summation of all mass exit. Yes or not, please? This is right. So when it is true, when there is a steady flow. When there is a steady flow. Now, second is steady state. Second is steady state. Very important. Second is steady state. The steady state. State is the property of the system. And what is the property of the system? Control volume, energy of the property of the system. So steady state, dE by dt of a control volume is equal to 0. This is for the steady state, very important. And here E is equal to m dot into theta. Yes or not? M dot into theta. And what is this theta? This theta is h plus v square by 2 plus z. Yes or not? This is your steady state. Now, if we combine steady flow, steady state, then this equation, so steady state, steady flow, so this mi, so these are the, if these are the steady flow, so this equation how we'll write? Summation of m into theta exit minus theta I, yes or not? Theta exit minus theta I, yes or not? And this is when we can write, this is for steady flow. Steady flow. And this is 0. This is 0 when there is a steady state. So how can we write? So if you combined steady flow, steady state, steady flow, steady state process. That means steady flow, steady state, steady flow, steady state energy equation. Okay. So in this condition, what is that? See this one. This is 0. So Q plus summation of all mass into theta I is equal to W kept out this in this right side plus m dot, this is m dot into theta E. So what we can write here? Q dot plus summation of I m into theta I, okay, is equal to W dot plus summation of exit m theta. Yes or not? Yes or not? So what we can write here in general, Q dot plus summation of all inlet m h plus v square by 2 plus zz is equal to work plus summation of all exit m h plus v square by 2 plus zz. So this is your energy equation for the steady flow. So this is your steady flow energy equation. This is called steady flow energy equation, or you call combined steady state steady flow energy equation. You can say that. You can say that like. Okay. So what is now this equation, what is the assumption? We already did this. So the what assumption is, number first, what is the assumptions beta? Number first, properties are uniform over a cross section. Number first. Number second, flow is steady. Number third, steady state with steady flow. Number first, what is the assumption? Properties are uniform across each cross section, each flow section, you can write each flow section. Okay. Number second, steady flow. Steady flow, that means dmcv by dt is equal to 0. And third one is steady flow, steady, that means steady state with steady flow, with steady flow, that means dEcb by dt is equal to 0. These are the three assumptions in which the steady flow energy equation are applied. They are very important. So these are the assumptions, okay? These are the assumptions, okay? These are the assumptions. Now, so these are the steady flow energy equation. Now, if we write, what we can say that, if we write like that, if there is a single inlet or single exit, if there is a single inlet and single exit, yes or not? So if there is a single inlet or single exit, that means mi or me, and mi and me is equal to 0 when the flow is steady. That means mi is equal to me is equal to m. This is very important. That means single stream, that means we can write like that, for a, like that beta, if we can write like that, for a single stream device, for a single stream device, that means single inlet, that means single inlet, that means what is m dot I single is equal to m dot E is equal to m. So what is the equation now? The equation becomes q dot minus w is equal to m dot into He minus Hi plus VE square minus VI square by 2 plus Z ZE minus ZI. Very important, I'm telling you. So this is for the single inlet and single exit. Right. Now, if you take a mass divided by mass, so this is your small q. Only q is there. Only q. Why? Because q dot, see, what is q dot? This is your joule per second. What is m dot? This is your kg per second. So if you divide joule per second into second by kg, so second by second, joule per kg, yes or not? So if you divide the mass minus W, this is your He minus Hi plus VE square minus VI square by 2 plus GZE minus ZI. So this, what is that, beta? This is the energy in the form of joule per kg. That means this is in the form of specific energy. This is very important. So this equation, it is in the form of joule per kg. It is in the form of joule per kg. That means energy per unit mass. Energy per unit mass basis. So this energy is per unit mass basis. This is very important. This is per unit mass. 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 Energy per unit mass basis. And this is your energy per unit time basis. This is your energy per unit time basis. So this is your energy per unit time. This is the energy per unit mass. This is your energy per unit time. This is your energy per unit mass. So energy per unit mass, see beta, this is your energy per unit mass. So energy per unit, and this is what, beta? V square. This is what? V square, that means velocity ka square. This is the component of velocity ka square. Velocity ka square, that means meter per second ka whole square. So joule per kg is something related to the meter per second ka whole square. How? Right. This is very important. Note. Joule per kg. Okay. What is joule? It is the energy. Energy is what? Force into displacement. That means Newton meter per kg. Now, what is Newton? What is Newton here? Here Newton is force. Force into mass into acceleration. That means kg into acceleration meter per second square into meter, this one, divided by kg. So this kg and this kg are cancelled. So what is that? Meter per second ka whole square. See the beauty. That means this is the specific energy, yes or not? That means specific energy, that means energy per unit mass, specific energy, that means energy per unit mass, and mind it, energy it in joule and mass is kg, is equivalent to velocity ka whole square, meter per second ka whole square. This is very important, I'm telling you. This is very important observation. Okay, this is very important. Okay, beta. Now, this is note number first. you have to write second note. Second note is 1 kilowatt hour. How much? These are the conversion every time in the question. 1 kilowatt hour. 1 kilowatt hour is equal to 3600 kilojoule. This is also important. Note number third. 1000 kg per meter cube is equal to 1 kg per liter, and this is density of water. Always remember this thing. Why? Because 90% gate question, in the 90% gate question, a student get confused here. Student get confused here. So this note is useful while you solving the PY gate question. While you solving the PY gate question. Okay. Now, so we have to complete the energy conversion of a control volume system. Now we will discuss about the application of this. One of the best application is throttling process. So what is the throttling process? Okay, what is the throttling process? Okay, what is the throttling process? Okay, what is the throttling process? See, my dear, throttling, that means you have to throttle of the fluid. That means this is your tube. Let's suppose this is one of the tube, throttling tube, and there is a throttling device. There is a throttling device. Add here. There is a throttling device. In the throttling, what we have to do? We have to reduce the pressure. We have to reduce the pressure. This is your throttling valve. This is your throttling valve, okay? And what is that? We have to close the valve. Gradually, we have to close the valve. If we close the valve, the area of the passage of the fluid which is in, let's suppose beta, this is at, let's suppose this is at inlet. This is at inlet cross section, and this is at exit cross section. Exit of the throttling and inlet of the throttling. So this is your inlet cross section, and this is your exit cross section, and this is your control valve. Okay, this is your control volume. Hi sir, Vasu Bhutia. Hi, how are you, Vasu? How are you? So if we have to reduce the section, if we reduce the section, the area will reduce. If the area will reduce, so this is the fluid is in here. The fluid is in here. Let's suppose this is the fluid in. This is the fluid in here. Okay, and here the fluid is exit. Okay, the fluid is exit. Okay, so this is your exit into the cross section, exit from the cross section. Okay, so fluid is in. I'm also fine, Vasu. I'm also fine. Okay, so fluid is in here, fluid is exit here, and this is our control volume. Now, if we reduce the passage, so there must be a pressure will reduce. If you reduce the passage, velocity increase, and when the velocity will increase, the pressure will reduce. Not understood. What is not understood, beta? Vasu, what is not understood? I think you joined late. No problem. You can revise the previous. You can revise the all. When this one throttling process, yeah. What do you think? This one steady flow. Huh? All. So you are regular from that time. You are steady with the initial time at 1 o'clock. The lecture will start. The lecture will start at 1 o'clock. Okay, Vasu. So if you, no sir. So yes. That's why you not understand. Please go through the all lectures. Previous lecture. It is approximately 1 hour lecture. Past 1 hour lecture. So all this thing we are cover. Okay. That's why you are not able to understand this. From here we covered all the things. Okay. So please watch the video. This is very helpful. Okay. This is very helpful. I am telling you all the things we will cover. So these are the throttling device. If we reduce the passage, you know that if we reduce the passage of the flow, the area will reduce, velocity will increase. Why? What is that? No problem. These are uploaded in the YouTube channel, and once you have to done it, you can watch previously. No, it is not here. No problem. Why? Because there is a working time. Students go to the schools, colleges, or all the things here. So that right now there is a very less people, but the views are very high when we have to come upload the lecture on the YouTube. Okay, no problem. You just watch and listen. So this is your. So if we reduce the area of the passage, the velocity will reduce. Once the velocity will increase, and once the velocity will increase, pressure will reduce. Okay. So if the pressure will reduce, that means during the throttling we reduce the pressure. This is very important. मतलब decrease the pressure. Pressure will decrease. Pressure will decrease. This is very important. Throttling is a process in which we reduce the pressure. It will reduce the pressure. Okay. Practical application of the throttling. Yes. Yes, Atul. Very good question. Practical application of the throttling process. Throttling process is the practical application when we reduce the pressure. That means, see, in the refrigerator, high pressure and low pressure device. So if there is a high pressure refrigerant, we'll have to reduce the low pressure refrigerant with no energy loss. With no energy loss. If you have no energy, if you want that no energy loss in the form of latent, so at that point the throttling is the process without reduce the energy. Why? Because you know that if the fluid is high pressure, and if you want to reduce it is on low pressure, there must be a drop in energy. But you don't want to sacrifice the energy drop. You have to sacrifice that. No, energy will remain same. That means what is the energy at inlet? The same energy. What is the energy at high pressure? The same energy we want at low pressure. So during that we have to throttle it. That means we have to successfully achieve that reduced pressure with the same energy. What is the same energy? Internal energy and plus flow energy. Okay, internal energy and flow energy. So basically throttling is the process in which we have to throttle. That means we reduce the pressure with no sacrifice of the energy losses. That is the practical application. I hope, Atul, you are clear. Okay. In the refrigerator we can use the throttling process. Okay. Okay, beta. So this is the throttling process. Now there is one inlet, one exit. That means Mi is equal to Me is equal to M. And we know that this is the steady flow device. What is the assumption? What is the background when we solve? What is the background when we have to study the throttling process, the background is that the throttling process is fully adiabatic. That means there is no chance of heat transfer. That means this is a fully adiabatic. All the things are adiabatic. That means no chance of heat transfer. So in the throttling, what is the parameter is fixed? No heat transfer. Q is equal to 0. And there is no any shaft work, pump work, there is no any work is involving. So work is also 0 by the control volume. These two parameter is fixed. Okay, these two parameter fixed. Now, there is no any motivation to increase or decrease the velocity. There is no any motivation to increase or decrease velocity. That means velocity at inlet is same as the velocity of exit. See, velocity within the throttling will increase, but it is at inlet, what is the velocity, and exit is far from the throttling valve. Exit is far from the throttling valve, so the exit velocity is normally equal to the inlet velocity. So in the throttling process, V inlet approximately equal to V exit. That means kinetic energy is also 0. Change in kinetic energy is also 0. Now, generally there is no any datum difference. What is the datum at inlet is the same as the datum at exit. So there is no any potential energy changes. So these are the few parameters which we have to consider. So what is the energy balance? We know that energy balance per unit mass basis, if you find the per unit mass basis, that Q minus W is equal to HE minus HI plus VE square minus VI square by 2 plus ZE minus ZI. Okay, no problem at all. Now, there is no heat transfer. Why? Because there is an adiabatic. There is no any work transfer. Why? Because there is no any working devices installed. There is no any change in kinetic energy, no any change in potential energy. See, my dear, this is very important. That means HE minus HI, that means delta H is approximately 0. That means the enthalpy at inlet of the throttling is the same as the enthalpy at exit of the throttling are approximately same. That means the enthalpy is what? Internal energy at inlet plus flow energy at inlet, internal energy at exit plus flow energy at exit. Yes or not? That means summation of internal energy plus flow energy at inlet is the same as the summation of internal energy at exit plus flow energy at exit. That means the energy content due to internally and due to the flow pressure. This energy is due to the pressure. That means what is the energy associated with the pressure and associated with the temperature? This is associated with the temperature. This energy associated with the pressure. That means energy associated with the temperature plus energy associated with the pressure at inlet to the throttling is the same as the energy associated with the temperature at exit plus energy associated with the pressure is same. Okay, that means enthalpy at exit is approximately same as the enthalpy at inlet. Enthalpy at inlet. Okay, enthalpy at inlet. That means you have to successfully reduce the pressure with no sacrification of the energy. Energy will same. That is the main advantage of the throttling. That is the main advantage of the throttling. Okay, so that means for the throttling, process, that means we have to reduce the pressure with no changes in energy. That means there is no any sacrifice of the energy component with reduction of the pressure. These are the beauty of the throttling. This is the beauty of the throttling. Okay, this is the beauty of the throttling. That means you have to reduce the pressure of the fluid from high pressure to a low pressure with the same energy. And that means, what is that? That means we cannot say this. That means, beta, if this is your throttling, see, very important, I'm telling you. If this is your throttling, one second, beta. If this is your throttling, okay, this is your throttling device, okay. If you throttle this one, beta, okay, if you throttle this one, okay. Now, if this, that means, see my dear, that means the fluid is in with pressure Pi, fluid is exit with pressure Pe. So the throttling will reduce the pressure Pe, but we don't know about the temperature. Temperature will increase, temperature may be decrease. This is very important. But the same enthalpy, that means enthalpy at inlet is the same as the enthalpy at exit. These are the very important thing. My dear, there are some confusion is that, sir, enthalpy is a isenthalpic process. Throttling is a isenthalpic process. That is okay, but which sense enthalpy at inlet is the same as the enthalpy at exit? So we can say that, and there is a very less chance to reduce the energy. That means in between them there is a very less chance to reduce the energy. That means energy, what is the energy at in and what is the energy at exit throughout the throttling is same. So in that manner we can say that the throttling is the isenthalpic process, but it is not necessary. Why? Because beta, it is enthalpy at inlet is the same as the enthalpy at exit. It is not necessary that enthalpy throughout the same. Yes, we will discuss in the next. Throttling and Joule-Thomson process are same. Very correct. But what is the approach here? We have to apply, Pratik, we have to apply the steady flow energy equation. So that we have to take in it. But the throttling in detail is a context of Joule-Thomson effect. Very good, Pratik. Joule-Thomson. According to Joule-Thomson experiment, we can achieve very different parameter for the throttling process, cooling and heating. Okay, but here we only apply the steady flow energy equation. Okay, and some inside advantage of the throttling. Why? Because this throttling is a device which is frequently used in the domestic refrigerator. Okay, so it is very important that beta, this is very important. I am telling you, this is very important. That means enthalpy before throttling is same as enthalpy after throttling. Enthalpy after throttling. But that doesn't means that enthalpy are remain same, remain constant throughout the process, remain constant throughout the process, so we cannot say the throttling is a exactly isenthalpy process. No, it is not like that. Okay, so if you do that, there must be a, see this observation, see this one, this is the very important throttling of an ideal gas. If we throttle beta, if you throttle the ideal gas, that means this is our throttling process and we have to throttle ideal gas. This is our ideal gas. Ideal gas. And we know that ideal gas H is equal to Cp dt. H is equal to Cp dt. Yes. So what is true and false, please? That means throttling of an ideal gas is approximately as the isothermal process. Pratik, it is true or false? It is true or false, please? It is true or false? No, it is false. You are wrong. This is the beauty. This is false. Ideal gas throttling, it is not isothalpy process. That's why throttling is a not isenthalpy process. This is very important. That means we can write here Hi is equal to He. That means enthalpy at inlet is same as the enthalpy at exit, but it is not necessary that enthalpy throughout the same. What is means by isenthalpy? See, a isenthalpy process. Isenthalpy process. That means enthalpy is constant. Yes or not? Throughout the process. That means at state 1, at state 2, at state 3, at infinite number of stages, it is constant. During the process, process I to E, process 1 to 2, during the process, the enthalpy is same. But throttling, it is a process in which this is Y, this is X. So this is your inlet 1, let's suppose, and this is your inlet exit. So at this point Hi is equal to He. It is not necessary that all point enthalpy is same. That why we cannot say that the throttling is the isenthalpy process. Yes, it is the during the throttling enthalpy at before entry to the throttling and enthalpy after exit from the throttling are same, but it is not necessary during the throttling the enthalpy is same. Okay. That's why we will discuss. Outlet product stream is more heated or cooled in the throttling. It will heat or cooled, but enthalpy remains same. See, enthalpy remains same. It is inlet or exit, not during beta. During the throttling, enthalpy is not same. But yes, if you take a fluid and you measure the enthalpy, if you take a fluid, you measure the enthalpy at inlet. And if you take that fluid at exit, you measure the enthalpy. Both are same. But it is not necessary during that process the enthalpy is same. It is not necessary. If it is necessary, then you can say that, sir, throttling of an isenthalpy process, throttling of an ideal gas is isothermal. No. That means What we may know that this is I and this is your E. That means H I is approximately HE, yes or not? That means CPTI, this is delta H, approximately CPTE, CP cancel, that means TI is approximately TE. That means if you draw, this is a T and S diagram, temperature and entropy diagram. Let's suppose this is inlet, let's suppose this is exit, very important, of an ideal gas. So at inlet and this is exit. So during the process, the temperature may be reduced, may be increased, or remains same. Anything. Temperature may be increased, temperature may be decreased, or remains same. But we cannot say vibration is decreased or increased due to the high pressure change, but input and output enthalpy remains same. Great. That means at this point the temperature Ti is the same as the T exit, but it is not necessary throughout. So we cannot say that this is the isothermal process. That means this statement is false. It is clear? It is clear? It is clear, yes or not, please? So if anyone asks you intuitionally, what is the throttling process? If the enthalpy is the same, you can say two lines. First is that, sir, yes, enthalpy before throttling and is equal to enthalpy after throttling. Yes, it is right. But it is not necessary that the enthalpy is throughout the same as inlet to exit. That's it. This is your answer. Okay, Pratik? Clear? Clear? Please? Clear? Yes or not? Yes or not? Okay. So these are the observation. Now we ended here, and so we can write here isenthalpy process. So throttling is not a approx. Okay? It is approx. Yes, if enthalpy is not remain throughout, then it will not follow law of conservation of mass and energy. No, it is not necessary. See, that means enthalpy at inlet, this is very important, is approximately equal to enthalpy at exit. Yes or not? Please, anyone? Yes or not? That means U at I plus Pi into Vi is approximately same U at exit plus PEV. Yes or not? Yes or not? That means beta, this is what? That means combination of internal energy plus flow work. Flow work is constant. Yes or not? Is constant. Yes or not? That means during the throttling, if we the summation of these two are constant, that means if internal energy will increase, see the beauty, internal energy increase, that means temperature will increase, the flow work must be reduced. These are the very important, so that the product is constant. If internal energy reduced, that means temperature reduced, you have to increase the flow work. Very important. Very important, I'm telling you. That means, very important. If there is any container, very important, I'm telling you, very, very important. If there is a container, and if in the container you have to increase the flow work, you have to increase the flow work, you have to increase the flow work. If you increase the flow work, that means if you charging the tank, increasing the flow work, its internal energy reduce. That means the fluid have reduced internal energy, that means it's have a cooled. That means during the charging, the fluid which is entry into it is cooled. Okay, that means if the increase the flow, but this is for what? It is just like a Bernoulli, in the Bernoulli, see beta, one thing is that Bernoulli's, in the Bernoulli's equation, this is also energy. I am giving you one insight things. If you think of Bernoulli like a throttling, there are two different aspects. If you do the conservation of energy during the, if you analyze the Bernoulli equation and apply the conservation of energy, that conservation of energy during that application, we have no bothering about the irreversibility. That means Bernoulli equation is applied for the reversible. That means there is no any viscous effect. The analysis of Bernoulli, there is no any viscous effect. There is no any irreversibility. There is no any dissipation. The energy at inlet, energy at same, exit is same. But in the case when we analyze the throttling is a highly irreversible process. That means there must be dissipation. So Bernoulli, you can, someone will say that, sir, you apply the Bernoulli equation in the throttling. No. Why? Because Bernoulli disregard the dissipation effect. Viscous. Bernoulli is applicable for inviscid fluid. But the throttling is, in the throttling we consider the irreversibility, it is formation, losses is there. Okay. So it is equivalent but not exactly. That means if you increase the flow work, internal energy will reduce. This is very important. This is very important, I'm telling you. Now, we have to prove during unsteady whether the temperature will reduce or increase. Let's see. But in this equation, if we decrease the flow work, internal energy should be increased so that the addition will constant. If we increase the flow work, internal energy should be decreased so that its summation is remain constant. Okay, so like that we have to, and that means, or we know that means during the throttling, internal energy may be increased or may be decreased. Yes or not? During the throttling, internal energy may be increased or may be decreased. And internal energy is a good representation of the temperature. That means during the throttling, temperature may be increased or may be decreased. This is very important. That means internal energy is a good representation of temperature. So temperature may be increased, may be decreased. Temperature may be increased, may be decreased, or remain same. This is very important. That means we can say that, means we can say that beta, during the throttling, what is the parameter? Q is equal to 0, work is equal to 0, change in kinetic energy is 0, change in potential energy is 0. Number second, enthalpy at inlet is approximately equal to enthalpy at exit. Number third observation, P at exit must be less than P at inlet. Number fourth observation, what is that? Temperature may be increased, may be decreased. These are the points you have to always remember during the throttling process. Okay. Now we have ended here. We will meet tomorrow. Okay. Next session. Okay. Thank you. Bye bye.